CLI and a cross-platform IDE for C and C++. Download now.
Hello everyone, my name is Ranjith Hegde, and this talk might seem a little unusual compared to the others that have happened so far. This is neither a tutorial nor an exploration of certain C++ concepts, as we usually expect. There will be a deep dive into a library I've been working on for the past year. But more importantly, one of the key takeaways here is appreciating a problem regarding coordination that's existed when it comes to multimedia, and especially when using languages like C++, how these can be solved, or at least attempted to solve in various ways. It's a problem that many different tools have tried to solve, but generally they are scoped to one particular domain, let's say audio or graphics or input. There are exceptions, of course, things like game engines, but even then, the domains are treated separately with different concerns instead of coordination. So with this talk, I aim to present the problem in a very specific way, and also in a very broad way, because my background is very different from that of a technical person, generally speaking. So I'll be exploring how I arrived at understanding these problems and how we can think about these problems, and then certain measures I took in my library to attempt to solve them. When it comes to synchronizing various domains, audio, graphics, for example, the key problem is that they run at different rates. You usually have a callback thread, a sync operation with audio, and the graphics loop, OpenGL, Vulkan, whatever you use, that has to run at a particular frame rate. And they are very different timings and also very different operations. Audio generally is just a simple callback function that you supply and the logic you decide, but the mechanism is you fill up buffers or you read buffers. With graphics, of course, there are various ways of handling this. In my library, I use Vulkan, and here we are dealing with render parsers, command buffers, so on and so forth. And with input, completely different. We basically are the event listeners for whenever we receive input from the devices we are tracking. And the fourth layer being whatever user code is and whatever the user is trying to do by synchronizing the 3, 4, or any subset of these issues. And trying to say that we can have one context, one while loop, where everything can be synchronized, has never really worked, primarily because they are all different timings. And if you are building a tool that works with all of these at the same time and not considering them separate, you need a mechanism to communicate between these independent processes. I choose coroutines, and we'll explore how and why in a bit. But you would generally need some variety of making sure that you're reading instructions from one side, communicating to the other side, reading data from the other. And if it involves cross-domain messaging, then you also need to figure out how and when you make a lock in order to read safely. At the same time, adding locks to audio thread. People have explored this for several years. It's generally a bad idea. Regardless of what sample rate you choose and what buffer sizes you choose, locks can be quite destructive depending on what it is that the user wants to do. And the ideal way for this, of course, is lock-free coordination. And you also need to ensure that if communication is involved, the timing that the user specifies as to when the communication should start and when it should end, or if it's a recursive pattern, that timing survives while you are crossing these domain boundaries. And specifically, if you're trying to say that you want to read audio and then send that to shaders, or the other way around, they all do not work with the same type. That's another problem to consider. And this is not a unique problem in any single domain. Whenever you involve coordination, you have to tackle with these concerns. Now, this is where I said it's not a usual talk because I do not come from a programming background or any kind of technical background whatsoever. I was a performing musician for a very long time. I played the violin and slowly drifted towards what's now called interdisciplinary performance. It's a kind of performance scheme where many different people from various disciplines are working together in a way where it doesn't matter what you started as. In the end, that identity is dissolved into something cohesive, something together. It's not about bringing tools from mine and integrating that with someone else's, but essentially entirely dissolving what movement is, what sound is. That is my starting point. But that move towards technology, when I tried to explore what happens if I try to add technology to my art, and that took me to Den Haag in the Netherlands, where I did my research, my master's research in gesture tracking and tendency systems. The tendency systems here refer to what kind of tendencies performers have, how can you track them, instead of tracking all their movement and trying to analyze everything. Try to be partial to certain things that you know a specific artist to do more often, or certain things that you found interesting in their previous work and try to recreate that, and tracking those, finding interesting patterns in those and using that instead of tracking everything. That was my thesis. This led me to developing audio for games, particularly Metro Awakening, that came out last year. And eventually I moved back to art, so to speak, by being a teaching faculty at Srishti in Bangalore. And one of the classes I was teaching there is interesting to the problem that we are discussing right now. I designed this course called Sculpting Noise, which was essentially trying to understand indeterminate systems, chaos systems in and around us. It could, from anything as simple as traffic to air traffic control to weather, disaster relief, anything at all that humans are involved in, where system theory can be applied. But understanding that through the lens of things inherently being nonlinear, things inherently being non-deterministic, and generally finding that collapse happens when people force linear solutions or discard nonlinear interactions with the system, which also led to examinations of different kinds of logical fallacies around synchronization. And this is the real overlap with coordination between various domains in programming as well, especially when it comes to timing, trying to see them as synchronous when they are necessarily asynchronous because of timing models, because of concurrency, and so many other things. I'm going to attempt to use C++ analogy here for what the interdisciplinary method meant, because what I used as an artist is directly relevant here when exploring code. Because when I said interdisciplinary and the idea of dissolution of identities, what I have here is what I mean. Right? Instead of saying that I'm taking a library and I'm using it by making certain calls, this process of interdisciplinary that we were working with is akin to inheriting classes, adding overloads that have nothing to do with what it started with, things of that nature. It's can be and usually is when it is in programming, but it's not the most perfect analogy, but this can give you a good mental model of what I mean and how that can apply to what we're about to discuss later. Everything comes down to a particular kind of negotiation between people involved. You propose something, the other person responds. You do not need to respond with what you started with. You can invite what they did, develop on that, and they can do the same. You allow enough options for other people to respond in different ways, and you take it from there. And in many ways, coordination between audio and graphics has similar of those. You cannot have silos of what's possible already based on historical precedents. you do not know what the user can do. And many of the tools that we use should generally try to segregate that, saying that if you use these methods, then you're safe. Otherwise, we don't know what. And this is also overlapping with my particular journey from hacking the violin by adding more strings, changing the word, various different things, to exploring electrical circuitry to see what that can do in terms of art. The first thing I did, if people are familiar with, called Eurorec modules, basically where you have patch bay and different tools like oscillators, filters, operational amplifiers, so on and so forth. You can connect between them, you can route them, and you create different kinds of sound. In particular, people, when this came out, were fascinated with the new possibilities that had nothing to do with acoustic. That is to say, not a replication of what you can do acoustically. It's not about building another violin that is electric, although that certainly happened and it's interesting, but also about what you can do when you completely embrace resistors, things of that nature, when you try to work with circuits directly and see what happens. For me, exploring that for a couple of years and then coming to computing and finding the tools that exist, it was very jarring because the transition from acoustic to electric and the things that opened up, I did not find that when exploring tools on the computer. What I did find was that whatever happened in the electrical domain was recreated using computing instead of just exploring what computing can do inherently. We had virtual of all the things that I discussed in the electrical domain, virtual oscillators, virtual Euroracks, virtual knobs, everything. It very, very closely resembled everything that happened in the electrical domain and not something new that we could explore. And this is also where it gets tricky because, as I said, I used to hack the violin. Just understanding the physicality of the instrument and trying to renegotiate that using different materials can yield interesting results. And people have done this. That's how different instruments come about. And this also goes for electrical components. Just there is a whole concept called circuit bending, voltage control techniques that essentially allow you to play with these tools in a way that you're questioning its construction and coming up with new methods of putting them together again and using them. In many of the sanitized tools that we use today, that logic is not that supported because you're primarily tweaking parameters that are exposed to you. If it's an open source tool, sure, you could just inherit things from there and carry on by extending it. But that's not always very convenient and also not a reasonable thing you can expect every user to be able to do. And this constraint is something that I kept thinking about when trying to use many of the modern tools, primarily ones that have GUI, that many of these decisions that are made, they could be open, they could be negotiated with, but nature of the tools means that you are given what you are given and you use it or you pick something else. There's not a lot of room for that kind of hacking. And this is an interesting thing when I said earlier about the single loop where you can put everything people have tried. It's the cascading problem that instrument builders often consider, that the decisions you make when you're building the instrument are your own. That should not affect the usage. You should not cascade these limitations that you come up with into usage. Sometimes there are physical restrictions, of course. You can only have so many strings, you have wood, or if you're building circuits, you can only fit so many things in one space. But those limitations should expose something creative or whatever it is the use case is, and not limit the usage based on that. And this is something luthiers, instrument builders have been considering for centuries, where every decision they make sure that they are not restricting anything, and if possible, open up new avenues. And this is the key thing here, that yes, there are bits that are involved and there are physical parameters of the computing, but by and large, what we as programmers interact with, there are no hard constraints the same way you have with analog circuits or with acoustic environments, where you don't have to, let's say, consider the materiality of anything. you are free to build what you want. So there are no hard truths here. Everything can and should be negotiated. That means that anything that you see that you do not agree with, there are better ways to implement it, or you'll be able to talk to the person who implemented what they did and understand their mind behind what went on into it. All these things are very fluid. They're not as static, or at least they don't need to have the same principles of pliability when it comes to computing. And this is where the whole idea of the for loop, the one single for loop that all encompasses everything that many softwares use, I personally find to collapse. You do not need to force everything to be in that. The computing world has limitations because we are still supplying to analog devices. Frames have a particular rate, audio has a particular rate, otherwise we will not be able to perceive them as such. But that is the output constraint. What the user has to do need not be bound to that. This is the same as the cascading principle that we discussed earlier. User does not need to supply things at frame rate. They supply it when they supply. We consume it at frame rate and we present it at frame rate. Even the consumption need not be at that rate, but that's a different discussion. Only at the output side, when we decide that this is going to the screen or this is going to the speakers, that's when many of these rates matter and how it's calculated. What the user has to supply has nothing to do with it. But we generally tend to force that also onto the user, where you are given a draw loop that executes at frame rate and everything has to fit in that model. And this is essentially the thing. The perception limitations that we have when we say that for something to be audio, it has to be this and that, historical, cultural, whatever the decision might be. For the computer, there is no such thing. It just evaluates numbers. So recognizing the difference between what is perceptual and what is not perceptual, in the sense it should not be forced onto computing or the other way around, is the key principle to carry forward. And there are historical precedents as to why we use multiple rates. The oldest one we can think about is video cameras and silent movies eventually having sound, primarily about how fast the reel should move and how fast the audio should tick. But this is not a problem we have today. Like I said earlier, this has just been resolved at the output stage. Everything else we don't worry about this particular problem. This is a quick appreciation and a little bit of critique of the tools that exist that have tried to solve these problems. The early days of Max Pure Data, if anyone's familiar, they very elegantly solved the scheduler problem and the interrupt problem. David Ciccarelli and Miller Bucket. But also, that problem does not exist anymore. We have different kinds of processors today, yet we are still using the same solutions. When it comes to processing, the primary idea here was simplicity. Anybody should be able to use it, and it should open pedagogy, which had happened. But at the same time, we are in the draw loop. I'll leave this here. There are more important things to consider. But just this is the idea that we have tools, we have different attempts at fixing the problem, but they had constraints primarily also because hardware was very different at the time. And the user expectations when people are coming from different domains was also different. We have modern tools that can have different solutions. And this for me is where I started writing my library roughly a year ago. While sitting down and writing code has been a year, it's been a journey of the last 15 years of trying to discover and rediscover different tools and negotiating with them and wanting to build different solutions and ideas that I've carried forward for the past 15 years. Although I am completely a self-taught programmer. I learned it while I was writing my thesis at Institute of Sonology, because some of the tools I was working with, I felt that they could do a little more specifically for my research. And it was just simplest for me to try and do it myself. I wasn't very successful at the time because it was very early into my programming journey. But around last year is when I felt comfortable enough, because I had already tried to rewrite a lot of systems Unreal Engine provided for audio for the game I was working on at the time, Metro Awakening. With that confidence and with what I was teaching at SRISD, I felt that, okay, maybe I can take a crack at solving some of these problems. This library that I'm building is called MayaFlux, and it starts with C++20 instead of all older ones, primarily because I needed coroutines. I'm making use of many other features, as you will see going forward, but the primary decision for C++20 was needing coroutines. In this library, all the domains are completely different. They have independent execution contexts, but what happens here is via communication, using coroutines to communicate different intent between different threads, different execution models. So for audio, I'm delegating to RT Audio, primarily because it's cross-platform and I do not need to worry about mastering Jack, mastering Wasapi, or Core Audio for Mac. It's one single solution, because at the end of the day, they all the need is I need to accept the devices, I need to work at that, look at the rates, set them, and give them a callback function. For graphics, it is Vulkan and specifically dynamic rendering, because the way MayaFlux handles it is all the things that require graphics presentation, they record sub-commands, and there is a primary command runner that aggregates everything and dispatches that to Vulkan, which is only possible via dynamic rendering. And for the communication, I'm using lock-free nodes here. What happens is that every individual unit of computing is called a node, which just does one value. If it's audio, it evaluates one sample. If it is graphics, it evaluates one frame. If it's input, it reads one input and activates itself. And how you register them is completely dynamic. You don't need to have it predetermined. And any domain can add any number of nodes. The way it's handled is this, what I have here. You do a registration, and then you check which nodes need processing, and you process them. And in every execution context, whether it be graphics or audio, the idea is the same. There's an abstraction called handlers, and they all have a task, a node, a buffer, and they all do exactly the same thing in terms of processing. This is one cycle of audio, and this is one cycle of graphics. The actual callback itself is very simple, because all the complexity is handled by individual callers and their processing context. As every node has its own processing context, every buffer has its own processing context. All the manager does here is call the process, and it moves on. And this is a small detail I thought I would include, because I'm sure I'm not the only one who is inconvenienced by the compiler lagging behind on macOS side, at least the one they supply with Xcode. For non-Apple, I just do atomic shared pointer, but I have to use hazard pointers when it comes to macOS because it's not supported yet. So even registering and reading from input devices, which is traditionally via mutex, I tried to not have mutexes even there. I think the only place where there are still mutexes in my library is when reading from files. I might be able to solve that better, but with my current knowledge and with my current experiences, as far as I've gotten, with that is to say, all the execution contexts that are real-time are lock-free. Specific hardware, specific file writing at the moment still not lock-free. Well, We discussed this earlier. Lock-free here is not simply about moving away from mutex as a general design principle. It's also because in the fast threads like audio, which happens 48,000 times a second, or if you're not going sample by sample, 48,000 divided by 512 times a second, locking here is going to be the death of audio. People have tried. You can try and experience it yourself. It is not going to work. In order for scheduling to survive and for it to still be able to communicate with other threads without collapsing, we have to go through these procedures. So this is the registration that I was speaking of earlier. How do you add a new entity? This is the same for buffers or anything else. There's a pending operation queue that you add to, and every frame, which I'll show in the next slide, checks for it, drains it, consumes it. So when it comes to adding, we acquire, and we're only going to wait when the queue is full, which is generally not the case because it's quite large. And in general, you won't have that many real-time hundreds of thousands of nodes being registered and unregistered. If any of this is a little too advanced and you want me to go a little slower, please let me know. So the process is called by the manager that I showed earlier, but there are these cards, pre and post process cards. Pre-process, we look for any registrations or unregistrations pending. And same with post. You clear them out so that next cycle you can look for them again. So at worst, you'll have one cycle. If the queue is completely full, this is what you need to wait for. If it's not possible in pre, it's certainly possible in post. So every new instruction that the user adds, depending on which abstraction they use, because nodes are one unit, buffers are whatever size you say, and those are the operations take to transpire. They all follow the same thing. You register them, process happens, but in pre, you check for them and then you train them. Yes. This I'm sure you've heard at the moment by many different talks you've gone through already in these sessions. But here's a quick reminder. Read all you need for acquire so that when you're adding, you know all the states, release of completion, and relax for counters. There is a subtle bug I discovered on ARM, which I'm not certain that I understand fully, but I got a undefined behavior when trying to use my library on Steam Deck or on Mac OS. This was primarily because of a race condition when engine was trying to set the state of a node while the node was trying to be registered. And I did not at the time have specific acquire release models. I simply went with relaxed, and then I had to rewrite it because of the bug I saw on ARM. And now we explore coroutines. The way I'm using coroutines in my library is basically it's a timing synchronization model, not simply about concurrency, but also about understanding and dispatching the time requests the user has. Let's say a user wants to evaluate certain things every 2 seconds or every 30 seconds or 3-4 times a second. I have many factory coroutines, but essentially everything happens through these. You write a function and then you have an awaiter. A sample delay here is the awaiter. You say how much time you want a particular function to wait before it executes the next in its logical sequence of events. And that is handled using coroutines. And how do I do this? There is just a counter. Every single tick of whichever backend. If it is audio backend, that is every single sample. If it is graphics backend, it is every single frame. It increments the counter, and then you just simply check if it is time to awake the coroutine. And if it is, then you evaluate that particular thing. And here, the important thing to consider is that the threads don't matter. The user creates the coroutine on the user thread, usually the main thread, unless they have threadings themselves. But whichever domain they register it with will be calling suspend or ready, which means that that particular evaluation of what needs to happen when it awakens happens on that particular thread. And domains are simply enums. We will explore them in a bit. When you decide which context it is, that particular backend consumes that. Because the coroutines themselves, they don't care. They don't understand domains. They don't understand timings. They just check if the number has been met, then they wake. Otherwise, they don't wake or terminate, depending on what it is the user is requested. And this is small one in action. There are many awaiters you can use depending on the intent of what it is that you were trying to say. And they can be multi-domain. It doesn't need to be that one coroutine is only audio. Although internally it matters, because basically whichever is the fastest wins, and that particular thread will evaluate it and update the timings. If you are trying to do both audio and video, then audio will take over because it does more often, and graphics cannot awaken at audio rate. So each of these are individual awaiters pre-written that you can use that has particular logic. And all of these are evaluated every sample or every frame depending on the backend. But it is completely asynchronous because nothing is being blocked, just the nature of how coroutines work. If you need to wait a particular samples, you use sound routine. If you want to wait particular frames, you use graphics routine. There are composed routines that are multi-rate as well. And here is essentially where you can say, start this instruction, send, start the sound, add a new frame to the graphics, load this texture. All of that, you can either sequence it literally or you can use coroutines. And moving on to the next concept, what we had discussed earlier is also that it's not simply the timing, but also the data type that they don't share. Audio prefers to work in double precision floats. You can use floats, but it is just better to use double depending on the kind of operations you're doing. And when it comes to graphics, it's U8 that people generally gravitate towards, or depending on the structure of the data, you will be using GLM. And this is where I'm using concepts where every data structure that is created can be multiple things based on these kinds of compositions. Processable data is what you need, and also contiguous data is what you need, which we'll see in the next slide. If those things are guaranteed, that particular function can be used in either of the contexts, audio or graphics. I'm using this in the PCH context so that it's just available for all files. But essentially, this is just small wrappers at the moment. Where it's simply about the organization scheme of the data that I'm registering. And based on that, which functions qualify and which functions don't. If you're purely dealing with integers or purely dealing with decimals, if you need to convert between GLM break 2 to double or the other way around is much trickier because then you need to decide what happens, which axes do they occupy, and if you don't care, then that's a default. And processable data is simply a collection of these. And contiguous is, you cannot convert between non-contiguous data types, at least not in the way I've written it. It's just simpler. If it's contiguous, then you can first write the memory order, if it's row major, column major, depending if it's a matrix, and then say how to interleave, how to deinterleave, how to combine, how to translate. And many operations simply ask you to specify the data type input and the data type output. And first, the function will see if it is possible, if the data types satisfy function body's requirements. And many of these concepts. So depending on the ordering of memory and contiguousness, you can convert between different types or not. Just simple tricks to make sure that regardless of which domain you're working with, the data can be sent between domains, cross domains. I think there was a talk at the Auto Developer Conference 2025 by Scott Carver that covered many similar topics, but that was purely audio, but essentially about using concepts directly to understand which functions can evaluate, which functions are fast path, which functions are hot path, so on and so forth. Worth checking out. And this is the trickiest for me personally. Variants and visitor patterns, yes, they have a lot of overhead. But at the same time, it is something that I have to contend with, that there will be runtime conversions. The only thing that I have done to make sure that this is not very expensive is to say that the conversion is only necessary when you're crossing domain boundaries. And they're absolutely not necessary otherwise. And there are fast paths to not have to worry about this. It looks ugly, I know, but at the same time, for real-time data conversion, I could not think of something better. This data variant is just one collection. And it is decided based on this, because you want to be able to introspect what data type lives in something without necessarily having to write a visitor whenever you want to query data every single time. That would defeat the entire purpose of flexibility. So every struct that requires that ND data that we just saw comes with these properties that you need to decide while you're creating it, so that introspection is much simpler and conversion from one type to the other can still preserve the original type, the later converted type, and back to the original type, and also avoid unnecessary visitors, or at least simplify the visitors. These are simply flags that you set saying that what kind of data you're using, what category does it belong to. I've just listed the most common. There are many other categories that we use. And the dimension just says how is the data ordered and in what way is it preserved. Just using these things and asking the user to send these, or even just calculating these, avoids significant amount of overhead when it comes to variants. And in general, this is just good data management when you're considering cross-domain synchronization. As long as you're keeping track of this, you always know which can convert, which is simpler, which is easier. There's just more dimensions. And there are manufactured versions to just automate that if the user does not want to manually do these. And the tricky part here is that it's not simply one kind of data conversion, only when you are in different domains. Within graphics, you will have multiple things that you need. If you're dealing with audio and spectral analysis, again, you're dealing with complex numbers and they have different requirements. If you're talking about 3D matrices and 2D textures, once again, you have different things. Categorically saying that transmutability between textures to vertices is not possible is not very attractive, and nor should that be encouraged. So having these kinds of categories while registering the data or at some point during the data process helps clarify that intent and write better functions of handling data conversion. I wanted to revisit coroutines here because I earlier felt that we did not cover enough. So this is the promise state that coroutines require. And again, once again, these are categorized based on domains. Some routine simply has this body. And because the coroutine says that the promise struct is constructed and you can have values in it to track, I'm using that also to have arbitrary metadata that user can set and keep track of updates over the course of various suspend and resume cycles. Any data that they set here is guaranteed to exist, and there are cached values if the coroutine is not awakened yet, so that you don't have to awaken the coroutine simply to read a value. And the tracking here is simply, as we discussed earlier, you decide the time, a number is incremented, and whenever that is a multiple of whatever condition you have set to understand the timing is evaluated, you awaken coroutine. And there are various flags that you can set primarily to sync. If, for instance, you're using multi-rate coroutines and both the graphics thread and audio thread are trying to operate on it, then this is where it matters. You can sync to the clock that owns this, or you can decide to say that different things are reading it at different rates, and that's fine. Sometimes it's also not necessary that these need to happen every sample. They could simply happen every buffer boundary. That is to say, if you're dealing with audio, while sample rate could be 44,100 or 48,000, very few hardware works that way. Generally, you chunk them in sizes of 64, 256, 512, so on and so forth. So even for coroutines, it could be useful, and it has been, at least for me, to say, instead of doing every sample, do it at every buffer boundary. So there are various state tracking mechanisms for that. So these are the awaiters, where you set the delay context, and only those particular backends that control them, those particular subsystems that control them, will call process on them at that decided boundary. So we are simply using the idea of what the awaiters are. They dispatch logic about when to awaken the coroutine, when to suspend it, using that as timing synchronization. And because the backends are guaranteed to run at a particular rate, or at least you can synchronize them to run at a particular rate by calculating delta time and many other tricks, these are very deterministic. And this is how the resume works. So these are just simple tracking. And then based on the delay context, you just check for the specific value and then resume it or not. The logic here is not necessarily complex. It's simply what it enables when you use coroutines as timing synchronization and what kind of communication it allows. And this is one of the things that comes across after the things we have discussed, all the things put together. An audio execution context can send data to the GPU simply by using something like this, where you acquire the node state and then you simply do a memcopy to GPU. This is just an upload to GPU, and then VK buffers and various different memory things in the backend consume it. The user simply does this. They supply an execution context, a node, and then they bind it, and the shader reads it. So audio can directly feed into the GPU and vice versa, simply because of these kinds of bindings. Even though the node ticks at audio rate, it doesn't matter because you are simply caching the values of what you need. Or if it depends on what the user wants, they could just write it into a buffer and consume them as and when they want. And push constants, if you are aware of graphics programming, are very small, 128. For anything larger, you use descriptor sets, which is basically a working buffer that you can send to the shader for operations with. And this is also where you can send matrices, any structured data. So if you're working with your own data abstraction that from what I showed before, and you still want that to evaluate at audio rate using those functions, but communicate it to the GPU, you would just bind it as structured data, provide the data introspection things that we saw earlier, and this will simply send it to the graphic card. I have an example coming up later that it illustrates exactly how that's happening. So these are for the nodes, and for larger things like buffers, it's essentially similar logic. You acquire one processing context output, and you bind it. And there are also methods where you can say where it is being evaluated doesn't matter. You should claim a snapshot of that output and then process it yourself, and that's also possible. So that whatever you are trying to read from is independent, and you are still processing without changing its state. This is useful when you say you have several different for example, audio oscillators that are running, where each frame or each sample, they're updating its internal phase. And then the graphics consumes it. It is consuming at a different rate, but you only want exactly at the boundaries and not at audio rate. Then you can claim a snapshot of its processing context, process it yourself without changing its state. Then you're not updating the phase unnecessarily, but you're still getting the rate values that you need without disturbing the audio. And the shader side, you simply use the push constants, do as you want. It's just a simple throwaway shader. It's nothing of consequence. The idea here is that it is just reading from the push constants that we saw earlier and proceeding with the regular calculations. Shader doesn't care where it's coming from as long as these things are available. So the various execution contexts, the various timings, none of that has anything to do with this. They simply execute what they're told. So you can have a simple function, and this is the key thing that you can find in my library, where you can convert any math as, it's essentially a lambda, any lambda that you want as graphics or audio, because of how these are evaluated based on the package you choose. And one single lambda can exist as both, updating audio, updating graphics, reading from input, regulating its internal state, and sending it to GPU or however you want to use it. And all of these are composed, this I said earlier, using these tokens. Depending on which thing you're trying to change, if it is nodes, nodes are either at audio rate, visual rate, event rate. Custom rate exists because I did not want to include it, but nothing is implemented in that side. And when it comes to coroutines, once again, you're deciding at what boundary they are being executed. And buffers are difficult because buffers carry large data. You should also be able to choose which device it executes on and not just the timing. And hence, these specific combinations exist where you can say it should evaluate at sample rate, but on the GPU and sequentially and not parallelly. Well, which that particular combination is very tricky to handle. You'll be able to compose which ones make sense and which ones don't. And the backend simply looks at which particular token you are setting and evaluates it. You're free to override the backend. There's a possibility that says add hook, and you can write your own processing hook there. And that's true for any boundary. Each node, you disagree with its processing function, add a lambda. You disagree with how the buffer processing chain happens, you can add a lambda. Every aspect of this is completely composable, completely introspectable at any given point in time. And this is for the user side, where you can simply say you want to define your own custom domains. You simply combine the nodes, the buffers, the coroutines into individual values. And I want to share a single example. In this particular example, what's happening is I have three different physical modeling simulations. One is simulating something called modal synthesis, that is different modes of vibrations that are coupled together. The second is a voice modeling simulation, where it's simply a bank of resonant filters. And the third one is a waveguide, which decides whether unidirectional or bidirectional, and based on that, it's either a string or a pipe. And all are communicating between each other, even though they have nothing to do with each other, and they're being fed to the GPU, where they are messing up the camera. This is not necessarily, let's say, an artistic example. This is primarily to show that any aspect of this can talk to anything without breaking the boundary. So you'll hear first voice modeling, which is very basic at the moment. It's not any AI trained model or such. It's simply a set of resonant filters, just a recursive function, several of them. And you'll hear modal synthesis and all of that combined to affect the graphics. Once again, it's not that you cannot replicate this anywhere else, those specific results, but the power of those kinds of combinations. The idea that any data can be sent to the GPU to do what you want with, and the data that you're reading will be evaluated at the rate it was decided upon by its backend, and you are able to consume it at the rate that your particular backend can consume it at. And the fact that any different kinds of physical modelings can overlap each other. In this particular example, the waveguide that was that was generating the sound was directly being sent to voice synthesizer so that it sounds something like a voice. Any and every concept here is completely composable and interchangeable. They can talk to each other without problems. This is still an evolving platform. I've been working with this part-time through my teaching jobs since the beginning, and the last 3 to 4 months full-time after I left my teaching position. So, and also consider that I arrived at computing much later. So if you look at the library, you might certainly find things that you would say, hey, this is not very intelligently written. It could be written better. So if you think so, please let me know. I'm happy to learn. I still have a long way to go, but this was my attempt at first recognizing that the problem here is coordination and not domain independence. Domains should be independent and you should try to communicate between them. And then various methods I use to bridge that gap. Thank you.